Today, we're going to do some small-scale diesel experiments, mostly for fun, but perhaps there's something we can learn from these experiments and apply them to our 719cc supercharged intercooled Kubota diesel that powers our lightweight semi-vintage Honda Insight. You never know, sometimes you can actually learn something just by having a bit of fun. So for the experiments, we're going to be using this low-cost 196cc 3-horsepower diesel engine that's been set up on our test bench. We're going to do some silly and serious experiments. For instance, can you use the exhaust from a vacuum cleaner to generate boost? And if nothing else, what effect will the forced air from our vacuum cleaner have on the engine? Also, will a different intake manifold have an effect on this engine? Well, we shall find out. Now, this is silly, but what would happen if we put a carburetor on this fuel-injected diesel engine? Well, that's easy. It'll destroy the engine, but let's do it and try not to destroy the engine. Now, this is interesting. What will happen if we feed the diesel engine vaporized water? Now, I'm not talking about vaporized water as fuel. Nope, we're going to allow the engine to ingest this vaporized water through the intake manifold along with the air. I think that'll be interesting for sure. Now, how about giving the engine a sniff of propane? That could be interesting. And finally, we'll try blending our own fuel from motor oil and gasoline. Folks say this works, but does it really? We will find out. Back in January, actually Season 4, Episode 3, we used this exact engine and test bench for some vegetable oil fuel experiments, and if you want to know a little bit more about this test bench, well, I'll refer you to that video. But here are the basics. We have the little diesel engine connected to a 120 or 140 amp alternator. This alternator allows us to put a significant load on the engine so we can see what effects different experiments have. Now, the alternator is certainly a major part of this rig. However, keep in mind we also need an actual load as well. Over on the side of the test bench, we have a 1700 watt load bank, and what this thing does is it converts the power developed by the alternator into heat. If you factor in the efficiency of the alternator, well, this 1700 load bank can absorb a little bit more than 2.5 horsepower from the engine. Now, calculating the actual horsepower that can be absorbed is difficult because you also have to factor in the efficiency of the alternator, and that can vary quite a bit. Anyway, today we're going to be running a medium load on the engine for all of our experiments, and we'll have the alternator pump out 70 amps into the load bank. This should put a decent load on the engine for sure. Over here is the control panel that we'll use to switch the various loads. Actually, this switch turns on the alternator, this one turns on the cooling fans, and these are all the load switches. Over here we have a simple method to measure engine RPM, and we covered how to make this simple tachometer in Season 4, Episode 3. Anyway, the engine RPM will be displayed on this meter here. The voltage from the alternator, well, it'll be on this meter, and the current or amps will be displayed on this meter. Over here we have a 4-channel thermocouple meter so we can watch the temperatures of various parts of the engine. As far as the temperatures go, we're going to monitor a few points on the cylinder head because, well, actually I don't know where the best location for the temperature measurement should be. The first spot we're going to look at is the temperature of the valve cover. Now, this area is not in direct airflow from the cooling system, so it may provide some interesting data. The next spot is over on the side of the cylinder head between the cooling tin and the actual cylinder head casing. And once again, I have no idea what to expect here. Now, under the cylinder head, there's a bolt available to attach our last cylinder head temperature probe. Now, between these 3 probes, we should be able to tell if our experiments are having an effect on the engine's temperature. Of course, we'll also be monitoring the exhaust gas temperature because on a diesel engine, the exhaust gas temp tells a lot about what's going on inside the combustion chamber. On this simple engine, well, I don't expect we'll do anything that will actually jeopardize this engine, but it's good to keep an eye on this nonetheless. Okay, well, let's roll cameras and get this party going. Well, these things happen. It looks like we busted one of the load switches. I'll deal with that later. Alright, let's energize the alternator. And now I'll go ahead and spin up the cooling fans for the resistive loads. So far, so good. Now let's engage each load. So as you can hear, the engine's struggling a little bit, and that makes me happy. So over here we can see the engine's running at about 2600 RPM, and the alternator's putting out 74 amps at about 14 volts. Now catching these numbers on camera is a bit tricky, and as you can see when I move the camera we have issues recording the data. Well, that's no problem. For the first baseline test, I'm also recording the data with these two additional cameras. So I'll let this engine chooch for about a half hour, and then we'll take a look at the temperatures. On this baseline test, we're running regular diesel fuel, and this engine has no modifications done to it at this point. Well, it looks like the exhaust gas temperatures have stabilized at 660 degrees Fahrenheit. The valve cover temperature is at 174 degrees. The probe on the side of the cylinder head is at 192 degrees, and the probe underneath the cylinder head is at 175. So the governor on this engine is controlled by loosening this knob, and that will allow a spring to force the governor to shut the engine off. Well, we want to keep the throttle in the same position throughout the tests, so I'm going to use this stick to push against the governor arm that's below the fuel tank to shut the engine off. Ah, that's better. So for the upcoming experiments, we're going to remove the intake manifold and the air filter assembly and replace them with a 3D printed manifold that I ginned up. You know, it's hard to say how much engineering went into this little engine, and I base that comment on the fact that this engine resembles the gasoline-powered Honda GX series of engines. You see, all the low-cost gasoline clone engines like the Predator and others are based on the Honda GX series of engines. Now, based on my ignorant observations, I think this engine may be a unique blend of gasoline clone engines, which is fascinating when you consider a lot of the stuff from a particular area of the Far East are just copies of successful Honda engines. Anyway, the shape of the intake port and the gaskets that are used are identical to the Predator 212cc engine, which means you can actually fit a Predator carburetor to this engine. Now, I don't recommend that, but we're going to give it a try a little bit later. So the purpose of the intake manifold on a diesel engine is to provide a way to install an air filter and nothing more. A diesel engine will run fine without a manifold, so in order to gather more data, I need to run this engine for about 20 minutes to see what the effects are with an open intake port. Fast forward a little bit and time's up. Let's see how the open port affected this engine. Well, the exhaust gas temperature dropped quite a bit and it's showing 40 degrees less. However, the cylinder head temps more or less remained the same. That's interesting. I reckon it's possible that the stock air filter may be too restrictive. Okay, so now we're going to install the 3D printed manifold that we'll need for the next few tests. This manifold is printed from ASA filament and it can tolerate the heat from the engine. I've used ASA plastic on a lot of parts in the past and it has excellent characteristics. And it doesn't seem to be affected by diesel fuel or gasoline. Actually, a major part of the fuel tank in the diesel-powered Honda Insight is made from ASA plastic, and after 6 months of use, it's been fine. Alright, once again I need to gather some new data since this manifold is a modification to the engine and I need to verify it doesn't alter the way the engine runs. Fast forward 17 minutes and we have some new data. Well, I would say that we're looking at no real difference, and that's great news. Now things are going to get interesting. Let's feed this engine some water vapor and see what that does. So for this water vapor experiment, we put together a high-tech bucket of water with a snorkel that'll connect to the 3D printed intake manifold. Inside the bucket, well, we have two ultrasonic water vaporizers. Now when these 24-volt vaporizers are energized, they'll magically convert the water into some sort of cloud of water vapor. Here, let me give you a better idea what's going to happen when I switch these thingies on. That's pretty cool. These vaporizers are sold on the Jungle site for about 12 bucks each, and they have multiple purposes. I reckon the most common use is to simulate some sort of magical potion for Halloween parties or something like that. Alright, our test rig is in place, and I'm going to start the engine and let it run for about 10 minutes. Then I'm going to put the lid on the bucket and activate the vaporizers. This should be interesting. Okay, so it's been 10 minutes. Let's have a look at the temps before we activate the system. Well, it all looks about normal. The exhaust gas temperatures are hovering near 620 degrees, which is what I expected. Now, let's turn on the vaporizer and see what happens. So as you can see, I put the lid on the bucket and the engine's now consuming the vaporized water. Now there are a few holes in the side of the bucket to allow the air to flow into the bucket, in case you're wondering. Anyway, this particular test took a long time because it had interesting results. With the two vaporizers running, the exhaust gas temperature dropped from 620 to 600 degrees, which is not really awesome, but it's a drop in temperature nonetheless. Now with one of the vaporizers unplugged, well, the exhaust gas temperatures went up a little bit and hovered near 610 degrees. Now on video, this only takes a few seconds, but in real time I ran this test for well over an hour. It turns out that the cooling effect of the vapor does not instantly cause the exhaust gas temperatures to drop. Instead, with this test setup, it takes several minutes to see the effects to start happening. So, on a small scale engine, yeah, it's possible to reduce the exhaust gas temperatures with a couple of ultrasonic water vaporizers. But keep in mind, the speed in which the temperatures drop is not very remarkable, and this setup wouldn't translate well to full scale unless we use many more vaporizers. So, that's interesting. Alright, well, let's see if we can give this engine some boost with alternative methods. Okay, well, before we bring in the big guns, let's try something for the sake of, just trying something. So what we got here is a mattress inflation pump. If you squint your eyes and drop your IQ a little bit, it actually looks like a turbocharger. Well, it makes plenty of noise, so no. I'm not going to show you the highlights of the half-hour video we shot testing this thing. Long story short, well, this little turbo makes zero boost and it has zero effect on the engine. Now, using the exhaust port of a shop vac for boost is the textbook definition of stupid charger. Okay. Well, let's see if that's true. Now, in case you didn't know, a shop vac can move a lot of air, but it's not capable of generating any pressurized air, or as I say, boost. So that's probably going to be an issue. Now, if the shop vac did develop boost, any boost whatsoever, even a tiny bit, well, we would see a drop in the exhaust gas temperatures. Now, lean burning diesel engines, they love boost, and a little extra air in the cylinders won't harm this engine one bit. So the engine's still warming up, and already we can see the exhaust gas temperatures are on the rise. Let's give it a few more minutes and see what happens. Well, the exhaust gas temperatures more or less stayed the same. Actually, they went up a little bit. So I guess we could escalate this situation and use a leaf blower, but I can guarantee you that's not going to make a difference. Oh well, it was worth a shot. Let's try making our own fuel and see if this little engine will run on a home-brewed concoction. Okay, well, off camera I went ahead and removed the fuel tank from the engine because for this experiment, we'll need to manage the fuel with a little bit more precision. The engine's been run for about 25 minutes on regular diesel fuel just to get everything warmed up. Alright, well, let's talk about the fuel that we're going to use. Now, typically, homemade diesel fuel is made with used motor oil. However, on our first attempt, we're going to use fresh motor oil. Once we figure out what works, then we can mix a batch with used oil. But for now, I want to use clean ingredients. Now, what we're going to make is called the universal mix, and that's 80% motor oil mixed with 20% unleaded gasoline. So to begin with, we're going to mix up 1 liter of fuel with 800 cc's of motor oil and 200 cc's of gasoline, and that makes 1000 cc's of fuel, or 1 liter. Of course, this concoction needs to be mixed really well, so we're going to be using a homemade homogenizer to mechanically mix this substance. This thingy is basically a bucket with some tubing in it, and all we're going to do is circulate the fluid in and out of the bucket for about an hour to thoroughly mix the fuel without inducing a lot of air bubbles. In theory, as the fluid circulates, the pump will be doing all the blending. Let's see if this works. I'm going to go ahead and dump this fuel batch into the bucket and then turn the pump on so it can start to circulate. There we go. And I'll go ahead and let this run for about an hour. Fast forward 1 hour and our fuel is thoroughly mixed. Let me dump this mixture into a container and it looks like the container doesn't hold a full liter. Interesting. Alright, our test rig has been loaded up with the 80-20 mix and the fuel lines have been purged of any air. Now, there is still a little bit of pure diesel fuel in the injector pump, so it'll likely take a few moments after the engine starts for this mixture to be ingested by the engine. Let's see what happens. Well, it sounds like the mixture has reached the injector pump, and quite frankly, I don't think this engine likes it. But it's still running, so that's interesting. Over at the tachometer, we can see the engine is struggling to maintain 2000 RPM. We really should be seeing 2700 RPM with no load on the engine. So things are not looking good. Let's make things worse and put a load on the engine. Now, I'm not sure we can run a full load at this point, so I'm going to shut up and let you hear this engine struggle. So no dice. This universal blend of 80% motor oil and 20% gasoline is not going to work on this engine. So in this beaker, we have 400 cc's of 80-20 mix, and just for giggles, let's add 250 cc's of pure diesel juice. This will make the mixture mostly homemade fuel with a splash of real fuel. This time around, I'm going to use a 10mm wrench to mix the batch, and in a pinch, a 12mm wrench will also work. And the engine's running again. This time it's running a lot better and it can hold a full load. Now, this is interesting. The RPMs are a little bit lower. Keep in mind, we have not touched the throttle settings, and this engine should be running at 2600 RPM with a 70 amp load. Now, with regular diesel fuel, the exhaust gas temperatures were running at 620 degrees. However, with this hybrid fuel, we're seeing almost a 60-degree rise in temp. Oh yeah, it looks like this thermocouple probe didn't like the vibrations, and now it's broken. Meh, this sucks. I need to do something different. But before I go ahead and re-engineer the fuel, let's see if this engine will cold start on this mixture. So for the last 2 hours, we've been blowing air across the engine to bring it back to room temperature, which is about 100 degrees today. So yeah, it's hot in the shop. Let's see if this engine will start on this mixture. Not too shabby. I had doubts, but she fired right up. Now I'm going to have to do some homework and figure out what we can come up with for a fuel blend that works almost as good as regular diesel fuel. So let's move on and try a different experiment. Okay, well, let's try shooting some propane into the engine and see what that does. Now, just to be clear, the engine is now running on regular diesel fuel and not the 80-20 mix. So as I slowly open the valve, you may be able to actually hear the engine smooth out. The exhaust gas temperatures are going down and the engine is actually running a lot better, but I'm hearing a different noise and I'm not sure how to interpret that. It almost sounds like the engine is knocking. Over on this side, I can smell the exhaust and it actually smells a lot better, but I can detect a slight aroma of propane. Interesting. The governor is trying to maintain the set RPM, and it's hard to tell, but I think the engine is actually making more power. The knocking sound is unsettling though. From what I've read online, propane has a higher octane rating and it won't ignite until the diesel fuel ignites. Then it'll burn and it actually enhances the combustion process. The fact that I can detect the aroma of propane in the exhaust is interesting. Perhaps I'm giving the engine too much propane. It's hard to say. This propane experiment is interesting, however I don't want to destroy the engine yet. What do the experts think? I would love to hear your opinion in the comments. Alright, let's put a carburetor on this engine. Okay, so this is not a good idea, and in this experiment the carburetor will not have any fuel in it, because if it did, it would destroy the engine. You see, on a diesel, the fuel is injected by this pump and the timing is critical. This pump is connected to the crankshaft via timing gears and the fuel is injected into the cylinder head at the exact right moment for the combustion to occur. So if the carburetor actually had fuel in it, well, it would distribute the fuel willy-nilly and it would upset the timing and all that. So that's why we're not going to be running any fuel in this carburetor. Now in this experiment, we have the throttle wired wide open and we won't be touching that at all. Instead, we'll just fiddle with the choke and see what happens when we choke off the air supply going into the engine. This should make the engine very unhappy. Ah yes, the engine is not happy. The governor is trying to maintain the set RPM and the exhaust gas temperatures are going up. Poor thing, I'm so sorry. Let's let the engine breathe. Okay, now the exhaust gas temperatures are going down and the engine's just a little bit more happier. So putting a carburetor on a diesel engine is plain stupid. However, I was able to show that restricting the airflow by closing the choke caused the exhaust gas temperatures to rise. Now, on a diesel, anything you can do to keep the exhaust gas temperatures as low as possible is a good thing for performance and fuel economy. In this experiment, we can show that something like a dirty air filter or restrictive intake plumbing can elevate the EGTs on a normally aspirated diesel engine. You know, after playing around with this little engine today, I feel like there's plenty more experiments that need to happen. Also, I need to go back and focus a little bit more on the propane and the water vapor experiment, perhaps even combine the two. As for the homemade fuel, well, the 80-20 universal mix just won't work on this engine without diluting it with diesel fuel. But it's not over. I just need to do a little bit more experimentation and dial in the right mixture. Now, it would be nice to figure out what works on this engine because I have plenty of used motor oil that's potentially free fuel if I can get this engine to run properly on it. I had fun today, and I actually learned a few things. Hopefully you did as well. Thanks for staying till the end, and I'll see you next time. Until then.